Hey everyone, I'm DeCoste, and I want to talk to you guys about masks and how they work. I have my son Nathan here to help me out today. So first thing is, masks are made up of a bunch of individual threads that are either woven together or stuck together randomly. NIST actually put together a bunch of really cool microscopy images, which you can see here, that actually show the gaps between a variety of different types of different masks. And what you can see is most of the fibers are tightly wound together, and the gaps in between them are really, really small. On the larger end, they're somewhere between 30 and 50 microns. Behind me, I have a Lacrosse net to demonstrate the ratio of those gaps versus a variety of different respiratory particles. So we know the COVID-19 virus has to travel on a respiratory particle. It cannot go transport along by itself. Those particles are actually a distribution in size. Most of them, about 90% of them, are between 20 and 200 microns in size. The average particle size is somewhere between 70 and 90 microns, which is about the size of this soccer ball in relationship to the holes on the net. So let me show you what happens when we try to put a soccer ball through those holes. Nathan, can you help me? Right, what happens when we try to put a soccer ball through those holes? It gets stopped every time. Now what happens if we use the smaller respiratory particles? Do you think we can get any of these through these holes? Let's see what we can do. How about a 50 micron? How about 20 microns? What do you think about a 30 micron? I'm seeing pretty much all of them get stopped. Now the ping pong balls are much, much closer in size, and one of these may go through. So what you notice is if they do go through, which none of them did, they would get slowed up significantly, which is how a mask near my face slows down all the particles that are going toward it. So one of the other considerations is respiratory droplets that are slightly smaller than the holes and might get through actually will get caught up in the holes. So while these usually get expelled from our mouth at about 1 meter per second, while something that's close in size might get through as it pushes through, it's actually going to at least be slowed up. So it's not going to be going at the same speed, but it's going to get slowed up and lots of times just knocked right down to the ground. Now, respiratory droplets start as a certain sphere size, but they don't stay the same size as they move through space. So after you breathe it out, it's going to start moving across space, and it's going to actually start contracting as it's evaporating. So it's actually losing water as it moves across space. At the same time, a second phenomenon is happening. It doesn't stay at the same height, it's also moving downwards. So our particles that might start as 200 microns at the height of your mouth are actually going to get smaller and start to move downward. This is where we get things like the 6-foot social distancing rule. We've started to figure out how long and far those respiratory particles will travel and still be able to be breathed in by someone near you. All right, so by the time the particles have started to evaporate, they become incredibly tiny. And we can think about those again, there's going to be a distribution, but those are now gotten to the point where they might be about the size of a marble or even smaller carrying the virus particle. So now when they get towards your mask, you have to think about what does a marble do when going toward the lacrosse net. So Nathan and Amelia, can you throw the marbles towards the net for me? Let's see. I think every single one of those marbles went through the net.
Yeah,
some of them might have been slowed up and may not have gone as far as they would have, but when the particle gets so much smaller, it goes through your mask much easier. So the other thing that's been talked about in the context of masks is whether or not the masks allow you to breathe freely. Now here I have an oxygen molecule and a carbon dioxide molecule. Carbon dioxide is what we breathe out. Oxygen is what we want to breathe in. Now, when we think about these relative to the size of the pores in a mask, if you remember earlier I said those are about 30 to 50 microns gaps in between those holes. So if you want to know about the size of carbon dioxide, which is the larger of these two molecules, this is 0.3 nanometers, which is 100,000 times smaller in size than the gaps that we're talking about in the masks. Now, if you want to put that into some perspective, I have a little dot here in the middle of the paper, and you may not even be able to see it. It's a 1 millimeter dot. To put that into perspective, if I put this onto the football field behind me, which is about 100 yards or 100 meters in length, that's the ratio of size that we're talking about here. This one little dot does not get held up by something that's the size of the football field behind us. So let's summarize the key points here. Your mask is made up of fabric. That fabric is going to have gaps in them. The largest gaps in those are usually between 30 and 50 microns in size. 95% of the droplets that we exhale are larger than 20 microns in size. Therefore, most of the droplets that we exhale are actually going to be knocked down, absorbed, or at least slowed down by your mask in some form. And what that does is that protects everyone else that's around you. On the other hand, if someone is not wearing a mask, the unimpeded droplets that they exhale can travel up to 6 feet before they're evaporated or completely fall to the ground. These droplets now become smaller as they evaporate, and they will not be as easily stopped by someone else's mask. Therefore, I cannot wear a mask hoping to be protected from others around me who are not wearing masks. Now, when we talk about gas molecules like carbon dioxide and oxygen, these again are way smaller than the gaps in the mask. Like I said before, up to 100,000 times smaller. Now what that means is these gases, carbon dioxide that I'm exhaling and oxygen that I'm trying to inhale, can freely flow through the mask really readily. So in conclusion, what you need is for me to wear my mask, and what I need is for you to wear your mask. And we have to remember that we're all in this together, and the only way to get out of this is by protecting each other.